In today's video, we will study the fundamental theorem of calculus. Or the FTC for short. This theorem is the most important consequence of calculus. It gives us a way of evaluating definite integrals. Right? The Riemann integral that we studied in a previous video, by relating a Riemann integral to an antiderivative. So in this video, we will state the fundamental theorem of calculus. There are actually two parts to it. We will state both of them. And then we will look at how we can use the fundamental theorem of calculus to evaluate Riemann integrals. Now, the fundamental theorem of calculus has two parts. Part 1 says if f of x is continuous over an interval a to b, and the function big F of x is defined by f of x equals the Riemann integral from a to b, a to x of little f of t dt, then big F prime of x equals little f of x over the interval a to b. So that's the first part that relates an antiderivative to a function, or to a Riemann integral, rather. Part 2. If f is continuous over the interval a to b, and big F of x is any antiderivative of little f of x, then the integral from a to b of little f of x dx is equal to big F of b minus big F of a. This, when people think of the fundamental theorem of calculus, it's usually part 2 that they're thinking of. So this is interesting. This says, to evaluate a Riemann integral, first find any antiderivative of little f. Then evaluate that from a to b, meaning it's f of b minus f of a. And now let's look at several examples to see how this is applied. All right. First, we're going to want to find the derivative of the integral from x to 2x of t cubed dt. Now, this is going to be using the first part of the fundamental theorem. Now, what we're going to do is say let big F of x equal the derivative from x to 0 of t cubed dt plus the antiderivative from 0 to 2x of t cubed dt. This will equal the integral from 0 to 2x of t cubed dt minus the integral 0 to x of t cubed dt. Now, for this first one, let u equal 2x. Then what we get is big F of x is the integral from 0 to u of t cubed dt minus the integral from 0 to x of t cubed dt. This now means the derivative of f, which is d dx of our original integral, will be u cubed times u prime by chain rule minus x cubed. Now, u was 2x, so this is 8x cubed times, not 2x times 2, then minus x cubed. It's 16 minus 1, and we get 15x cubed as our derivative. Now, let's take a look at evaluating the integral from negative 2 to 2 of t squared minus 4 dt. This is part 2 of the fundamental theorem. It says first find an antiderivative. So we want to find the antiderivative of t squared minus 4. Well, that would be t cubed over 3 minus 4t. We can actually ignore the constant, right? Because we just want some antiderivative. So say the constant 0. This will now be evaluated from t equals negative 2 to 2. That means plug in 2 first. So we get 2 cubed over 3 minus 4 times 2 minus, now evaluated at negative 2. So negative 2 cubed over 3 minus 4 times negative 2. What we get is 8 thirds minus 8 plus 8 thirds plus 8. I'm sorry, minus 8. Right, it's 16 thirds minus 16. And this is negative 32 thirds. Right, now let's look at the integral, 1 to 9, x minus 1 over the square root of x dx. This is the integral from 1 to 9. Now what we can do is do x over root x, x to the 1/2, minus 1 over root x, which is x to the minus 1/2. Antiderivative would be 2 thirds x to the 3/2 minus 2x to the 1/2. Evaluate that from x equals 1 to 9. 2 thirds times 9 to the 3/2 minus 2 times 9 to the 1/2 minus 2 thirds times 1 to the 3/2 minus 2 times 1 to the 1/2. Square root of 9 is 3. 3 cubed is 27. 27 divided by 3 is 9. Times 2 is 18. Minus 6. Then we get minus 2 thirds plus 2. 18 minus 6 is 12, plus 2 is 14. This is 14 minus 2 thirds. Yep. So 14 times 3 is 52. No, 42. Yeah, 42 minus 2, we get 40 thirds. Integral from 0 to 1, x squared times 1 plus 2x cubed, all raised to the 5th power. Now, why don't we let u be equal to that 1 plus 2x cubed? This, of course, means that du is 6x squared dx. What we need to do is multiply by 6 and then divide by 6. Now look what we have. we have the 6x squared dx. That gets replaced with du. This becomes 1/6 the integral u to the 5th power du. Now what we have to do is find new bounds. Well, when x is 0, u is 1. Right? All I'm doing is plugging x equals 0 in up here. Then when x is 1, we get 1 plus 2, u is 3. So we have 1/6 the integral 1 to 3 of u to the 5th du. Integral of u to the, or antiderivative of u to the 5th is u to the 6th over 6. So we get u to the 6 over 36. Evaluated, u equals 1 to 3. We'll get 1/36 times 3 to the 6th power minus 1 to the 6th power. This is 1/36 times 729 minus 1. This gives us 728 over 36, which simplifies to 182 over 9. And finally, let's look at the integral 0 to 1 of x e to the 4x squared plus 3 dx. Again, u substitution, say u is 4x squared plus 3. Du is then 8x. So we have to multiply x by 8 and then divide by 8. Now we have the 8x dx. That gets replaced with du. We get 1/8 the integral of e to the u du. For the bounds, when x is 0, u is 3. It's 4 times 0 plus 3. When x is 1, u is 4 times 1 squared plus 3, which is 7. Antiderivative of e to the u is just e to the u. So that will be evaluated from 3 to 7. We get 1/8 e to the 7th minus e cubed. So we can just write that as e to the 7th minus e cubed over 8. Or we can factor out an e to the 4th over 8 and be left with e to the 4th. We're factoring out an e cubed. And we'll be left with e to the 4th minus 1. Either of these answers would be acceptable. That concludes the video on fundamental theorem of calculus. In the next video in this series, we will look at an application of integration known as area between curves. This is actually a real simple application since we already know that the integral represents a signed area. So I will see you all in the next video.